Welcome friends, I am Conway. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we will discuss about aromatic nucleophilic substitution, its basic concept and mechanism. Sorry for my unique voice, this is due to cold. Okay, so what we are going to learn today? We are going to learn about the basic concept and mechanism, and today's discussion will mainly focus few points. For example, the basic concept, the reaction mechanism, the intermediate which is named as Jackson-Messenheimer or sometimes Messenheimer intermediate, and mechanism for this process, and isolation of the intermediate which is the proof of the mechanism. Okay, and finally I shall provide the relative rate study from where you will get a complete understanding about the nature of nucleophile as well as living, as well as other factors. Okay, so let's start. So today we will start little different way. For example, today's talk will start based on some examples. What type of examples? If you treat this chloronitrophenol derivative, okay, so chloronitrophenol derivative with different amount of C, everything is same. This bicarbonate is same for everywhere. Okay, and only what varies, that is temperature. This is 135 degree, this is 100 degree, this is 35 degree, and here also temperature it's not mentioned exactly, but heat is given. So what is the product? What happens? This reaction produces 4-nitrophenol. And by the way, actually, okay, I will explain slowly. This second step product means 2,4-dinitrochlorobenzene resulted in, after workup, 2,4-dinitrophenol. This is dinitrophenol. Okay. The third one, 2,4,6-trinitrochlorobenzene resulted in 2,4,6-trinitrophenol. Okay, after workup. And this molecule has another unique name also. This named as picric acid. I guess you have heard about this. Picric acid. Why this is acid? Because of the presence of this 3-nitro group, its acidity is significantly higher. That's why this is called picric acid. Okay, this is trinitrophenol. And the fourth one, actually 3, or actually better to say, this is paranitrophenol. This could be another name. This could be ortho-para-dinitrophenol. Ortho-para. Actually, it's a trivial name. Okay, trinitrophenol, and this is meta-nitrophenol. Okay, or 3-nitrophenol. Sorry, this I guess I made mistake. This is 4-para-nitrochlorobenzene. This is ortho-para-dinitrochlorobenzene. This is ortho-para-trinitrochlorobenzene, and this is meta-nitrochlorobenzene. Okay, this could be the trivial name. Better to say that 4-nitrochlorobenzene, 2,4-dinitrochlorobenzene, 2,4,6-trinitrochlorobenzene, and 3-nitrochlorobenzene. And in this case, no reaction. This is the interesting one. Okay, so this is the observation. So initially, what is expected? What this nitro group actually doing? If you draw the structure of this starting material little better way, this looks like nitro looks like this. Okay, and we know nitro is a very strong withdrawing effect. It can produce minus I as well as minus R effect. In case of aromatic electrophilic substitution, this part I have explained in details. I have uploaded video about it previously, so please go through it. So minus R, minus I effect, and what happens that if you draw the canonical structure of this, you can expect that it will withdraw electron here, it will open. So what is the conclusion? This is chloro, this is plus charge here, this is nitro, double bond O minus, this is plus. Let's draw another canonical form. This is in what do I am saying? this bond will come here. So this is minus, minus, this is plus, this chloro, this is plus charge. We can think that since this chlorine has lone pair, these lone pair would be donated and the intermediate would be stabilized. Okay, so we can think that it would be another chemical form why I am writing, because it will help you to understand the process clearly. Okay, this Cl plus. 2 lone pair left. So all such type of resonance possible. What do I mean by these resonance structures? I want to give you an answer that overall, if we draw this molecule again, these O minus, sorry, it's better to write in a simple form. This paranitrophenol derivative, paranitrophenol derivative introduces plus charge here, here and here. Actually, the ortho and para position with respect to this nitrobenzene is electron deficient. And what this bicarbonate is doing? Sodium bicarbonate plus water. Okay, what it does, it's generating sodium hydroxide, or or better we can say it is generating hydroxide, which is acting as nucleophile minus negative charge. So fine, this nucleophile is generated and that nucleophile is attacking at the center. Okay, you may think that why this is attacking at this center? It can attack the ortho position also, because ortho position is also electron deficient. Fine, but that attack may be done, but after that what will be the consequence? Okay, after that what will be the consequence? Actually, attack may be possible, but since this is a substitution reaction, so we need something which can leave, and actually here this chloride can leave. Fine, so that's why the attack will be on this para position. So what will happen? It will come, it will go, and if we write this nitro part little more carefully, O minus, this is plus. So this will come here, after that it will come here, after that it will come. I am skipping every resonance structure, okay? So that I have just drawn sometime before the resonancing, you try by yourself. So this is the chloro, this is the OH. Fine. So we can think this, the most stable one is O minus N O minus plus. Fine. So what in next step happens? In next step, the negative charge which is held by the nitro group is pushed back. This. And now two chances are there. These OH can leave. If OH can leave, there is no reaction. Fine. Apart from that, Cl can leave. Why? Because number one, Cl is a relatively beta leaving group. Why I am mentioning the word relatively? Okay, it has a reason. Because during substitution reaction, we say Cl is not a good leaving group. Bromide iodide is a good beta leaving group. That's why I am taking the word relatively. So this is relatively beta leaving group and it leaves. And if it leaves, what it resulted? It resulted in this is OH. Fine. This is nitro. This. So then we can think what I expected, C minus Cl minus. Okay. What we expected we got. Then what is the role of these H2O plus? A simple question. Why this H2O plus is needed? Okay. It is needed because, so since the nitro is electron withdrawing, what it can do? It can help to deprotect this OH to result in presence of base. What can happen? It can produce phenoxide. Why? Because it is actually, you can say this is a conjugated acid of this phenol. So why? Because it can help to stabilize the negative charge in this way. That is the reason that under this alkaline condition, these will not stop. It may further undergo deprotonation to this. That's why this workup is necessary. Fine. Now the question is, why this mononitro derivative? This mononitro derivative needs 135 degree centigrade, dinitro needs 100 degree centigrade, and trinitro needs 35 degree centigrade. Why there is an enhancement of reactivity due to the increment of number of nitro group in the ortho and para position. Okay. The reason is, as nitro group introduces electron deficiency in the ortho para position, first point, and second point, nitro group is electron withdrawing. So increasing more and more nitro group increases the electron deficiency in the benzene nucleus. Okay, benzene nucleus, and that's why which facilitates nucleophilic attack. Nucleophilic attack is encouraged. Okay, so this is the thing why the increasing nitro group from 2 to 3 reaction becomes easier. Okay, so what we have learned? First point, introduction of nitro group makes this ring electron deficient, and since it is electron deficient, so expected that it will undergo nucleophilic attack. Second, increasing the number of nitro group, so increases the extent of electron deficiency. That's why reaction becomes more and more facile, or reaction happens under relatively less drastic condition. Fine. So this two. But is there any selectivity for the position of nitro group? Yes. It is expected to be ortho or para. Ortho or para. Why? Because if you take this meta one, then no reaction. Why? Because we know that nitro group increases the positive charge density of its ortho para position. So with respect to this nitro group, this is the ortho and this is the para. So this position which is expected that nucleophile will attack is not holding that much amount of positive charge. Why I am saying that much amount? Because it is not holding that much amount of positive charge, because this C carbon attached with chlorine, so due to electronegativity difference, it is expected that there will be some amount of positive charge density, but that is not enough. So if it is enough, then why? Why about this? If we do the simple chlorobenzene to phenol in presence of NaHCO3, okay, if you heat, then you can expect that, okay, we can have phenol or phenoxide, second step work up, first step this, and second step H3O plus. You can expect that this will be produced, but actually this doesn't produce. Okay, and for this information, you can visit or you can see one of my video named about Dow process, conversion of chlorobenzene to phenol, and that process is a drastic process. Why? Because this is not sufficiently electron deficient. So a conclusion is drawn. What? That for such type of reaction, it is essential that nucleus should be electron deficient and the withdrawing group should be a proper position such that this reaction can happen smoothly. Okay, so this is the nucleophilic substitution or aromatic nucleophilic substitution. Okay. So this is the background knowledge I believe you need to have for this, and the mechanism part, how this reaction happened, I have explained. So from this study till now, so what we have learned, if we want to summarize this learning, we can say that in presence of an electron withdrawing withdrawing group benzene nucleus or aromatic nucleus, you can say, became susceptible for the attack of nucleophile, which is actually it is an electron rich molecule. Why I am saying electron rich molecule? Okay, so why? Because electron repair. In my previous video about the difference of, that is the difference between the aliphatic CCl bond for nucleophilic substitution, aliphatic CCl bond versus aromatic, or you can say vinylic. So that case I have explained this factor because of, first let me give you a crude explanation. Please go through that video for details. So this is Cl, if it is. So if backside attack need to be done, will be hindered by the pi cloud. Okay, pi cloud. Front side not possible because of the lone pair of chlorine. Okay. So this, and another thing, the most important thing, multiple bond character between this. Why and how? If you see, it has these 3 bonds. So if this chlorine delocalizes its lone pair here, it will be here, this negative charge, then it will push, then negative charge will be here, then it will push, negative charge will be here. Conclusion, this chlorine has, and this became a double bond with a plus charge. What does it indicate? This is the third point. This is the first point, pi cloud. This is second point. This is third point. Cl carbon multiple bond. And what does it mean? Multiple bond means stronger bond. Okay, so stronger bond. If it is stronger bond, then it is difficult to break. So we have understood the problem. How to solve this problem? By introduction of an electron withdrawing group. Why? Because electron withdrawing group introduces electron deficiency, and that electron deficiency facilitates the attack by an electron rich molecule. Okay, got it? I repeat. This is an electron rich molecule. How to make this system susceptible for nucleophilic attack? First, attach an electron withdrawing group. If we attach an electron withdrawing group, then this nucleus became electron deficient, and because of this electron deficiency, nucleophile can attack, and that electron withdrawing group's position should be ortho or para. Okay? Okay, fine. So ortho or para. What are the other different electron withdrawing groups? Apart from nitro, we can say cyano, we can say carboxylic, ester or acid, whatever you say. We can say carbonyl. This should be ketone or aldehyde, whatever both. Okay? So lots of this functionalization is expected to be possible. But these withdrawing reduces electron density in this benzene nucleus, that's which allows the incoming nucleophile to attack, and this attack is via a formation of a addition species. That means first step what happens, let's take the example of 4-nitrobenzene. In first step what it produces, the most stable one, this is this. Just I have explained previously, so I am not going to explain again. Fine. This, so for example, let's take RO-, alkoxide. Okay, alkoxide. So, and definitely there is some cation like potassium, you may think. This is a chloro, this is a OR, and along with that potassium plus, because this overall moiety, total moiety is a negative charge right now. And generally we forget to mention this cation. it is not a mistake that we forget to mention potassium, but we should keep it in mind. We should not forget that there is a cation. And if anyone asks you during the interview, you should say that there is a cation which we didn't write, but it is there. Fine. So what is happening in the next step? Next step, this is attacking. It is coming. It is attacking, and this leaving. So ultimately, it results in nitro, and we can say what? Ether. If we use alkoxide, is it essential to use acid? Directly say no, but indirectly say yes. Why? Because there may be some amount of excess alkoxide you need to neutralize. For that reason, you need to acid, but these will not form any alkoxide because there is no hydrogen, replaceable hydrogen. Okay, fine. So this, and actually this process, this overall reaction is divided into two steps. So first step is the attack of nucleophile. Attack of nucleophile. And second step is the leaving or departure of the leaving group. Leaving group departure. Okay, these two parts. So addition, elimination, both. And this is the intermediate of this process. So this is the intermediate, and this intermediate is named as this Jackson-Mesenheimer. Mesenheimer intermediate. Fine. So sometimes people only say Mesenheimer intermediate. Jackson they don't pronounce. So fine. This is Mesenheimer intermediate. So these Mesenheimer intermediate convert. So what is expected rate equation for this process? So if we write the rate equation is equal to the rate constant into the starting material, that is 4 Cl nitro, we can say para-chloronitrobenzene, and K plus OR minus. So this is the rate equation. Okay, and which one is the RD step? This step is the RD step. Why? Because here the nucleophile, this is attacking at this center, and for this process aromaticity is lost. Aromaticity is lost because of this attack. So what we expect, that the corresponding energy of activation for this process will be higher, and this part will be slower compared to this. Okay, I am saying it is difficult, but why it is easy? Because here a leaving group is going out and producing a aromatic molecule again. So this process is faster and easier compared to this. Fine. So that's why this process, this is the RD step of this process, and this is relatively faster. Okay, and rate equation is depending on the substrate, concentration of the substrate as well as alkali, because both are involved in this RD step. Okay, fine. Now, another point. Okay, better. I shall say. So this is the isolation. Okay, Mesenheimer complex I have told. Let's discuss about the isolation of intermediate. Now, in like general case, we always say as a proof of mechanism, it is better to isolate the intermediate, and this is true for this case also. Intermediate isolation supports the explanation for the mechanism. Okay, so for this purpose, a specially designed substrate. What is that? The substrate is, so this is nitro. This is nitro. Let me check. Yes, this is also nitro. This is nitro, and this is N-methyl
This is the substrate. Okay, so if you treat this substrate with ethoxide or methoxide, whatever, this, so what is expected? Where is the acidic proton present? This is the acidic proton. So alkoxide exchange, and it can produce the alkoxide from here. So or we can draw it little different. Let's draw it little different. You will have a better idea. And plus methanol, if it is a methoxide. So now this is nitro, and this is also nitro. Why I am writing it in different way? You will get it. Plus. Fine. So what can happen? This can attack here. Okay. So if it attacks, it opens up here. Then it will result this is O, this is minus NO2. So what is expected? That this is NO2. What is expected? That this nitro will be resonance stabilized by this group. Fine, we know, and that is the design substrate. First of all, this position carbon ion is stabilized. Another thing, instead of that, it can come here, and it will, negative charge will come here. So what is the canonical form? So this is the minus, this is NO minus, this is NO2, this is NO2, fine, and here this NMe, this, fine. So this negative charge can also be stabilized here. So what does it mean? That in this way the negative charge is stabilized. Actually what remains, the actual isolated structure of that molecule is this one. These are same, but still for your better understanding I will write the way I was writing. Fine. So this is the isolated intermediate, and obviously the corresponding salt, for example, if it is K plus, then it must be K plus. So this is the isolated intermediate. Okay, so this is the isolated intermediate, and this proves or supports the mesenchymal complex. Now you may think previously we have used chloride. Why we have used this? Because we have to trap the intermediate. If we have been used chloride, then after attacking of this chloride would have been gone from this side. Okay, so that is the reason we have to check that, okay, this is attached here, the oxygen attacked here, after that such type of, what canonical form we propose, we are getting actually here. It should be nitro. Okay, so this is the proof of this concept that reaction is following about this path. Okay, so at the end of this discussion I shall give some relative rate study. Okay, so we are at the end of our discussion. So now you can see that a table I have provided to you. Means this is a 4 halo nitrofenol. 4 halo nitrobenzene. Fine. And reacted with OMe methoxide, definitely some M plus is there. So what it resulted? when this X equal to fluoride, the reaction rate is 30. So when this X equal to iodide, the reaction rate is 1. Okay? When bromide, reaction rate is 2. When chloride, 3. When fluoride, 1300. Tremendously high. Okay? Question is why? Why from iodine to chlorine reaction rate increases? Okay? Because if you go from this side in this way, size increases and electronegativity decreases. Fine. So if size increases, what creates? Bigger size. So nucleophile is facing some static repulsion to attack this center. First point. Second point, what about the electronegativity factor? This attack resulted in a formation of an intermediate. What type of intermediate? Just I have drawn previously. This is O minus, this is plus, and this is OMe, this is X. This is Mesenheimer complex or Jackson-Mesenheimer complex. So this is, and in second step this is producing this. So first step this doesn't came here. First step this negative charge first came here, here and here, and this part is stabilized by this diameter. Okay. So if the X minus is sufficiently higher electronegative, then this will stabilize this. So these are the both two factors. Why exceptionally high for chlorine? Because very smaller size and the highest, actually we say highest electronegativity. Okay, among the series as well as among the periodic table, it is around 4.0 in Pauling scale. Fine. So that is the reason and that is the uniqueness of this concept. Okay. So this basic concept part and mechanism part is finished here. So in the next video I shall give you some example, real example, from where you will be able to understand about the process completely. So this is the end of the discussion. Thank you for listening my lecture. So if this video is useful for you, please share this video among your friends such that it may help that person. So in this way you can help also. So thank you. Stay happy, stay blessed. See you in my next video.